I'm Nick Callahan, and this is my CS491 final project on the Atari game Demon Attack. The basis of this Atari game, again called Demon Attack, is that the player controls a ship that's located towards the bottom of the screen, and it moves either left or right but not up or down, and sends out these blasts towards incoming demons. And the demons return blasts as well, and hitting one of the demons with the ship's blast provides a reward, increases the player's score, whereas if the demons hit the player, it reduces the player's lives. The player starts out with 3 lives. They can go up to 6, where they gain a life at the end of each set of demon waves. Other than that, the only way to lose the game is to run out of lives. The actions in this game are quite simple. There's a total of 6 options. The first is a no-op, so choosing not to move and choosing not to blast. The second is to exclusively blast but not move. The third and fourth options are to move but not blast, so you can either move left or right. And the final options are to move and blast at the same time. And down the line I will be representing the probability of each of these states with this sort of graph that's representing the probability that is output from the model. The default rewards, the default scoring mechanism, is fairly straightforward but still more complex than many games like Pong. Essentially, there are 3 demons per wave. There are 2 waves per level. After each set of 2 waves, after every 6 demons, the reward for killing a demon is increased by 5 points. Initially it starts at 10, increased by 5 up until a total of 35 per demon, which occurs after 12 waves. And there's an option to spawn split demons and diving demons, which are a little more dangerous to the player, and these have double the reward and quadruple the reward respectively. The pre-processing for this model is fairly standard, fairly similar to what we saw in the Pong code. Essentially, the 3-dimensional array is trimmed down to 2 dimensions, so it's essentially grayscale. Binary color palette where the background is one color and the actual objects, the agent and the demons in this image, are reduced to a second color. The vertical portion of the frame is downsampled by a factor of 2. However, it's not horizontally downsampled due to the fact that the width of the blasts are only 1 pixel wide, and so there would have to be a mechanism to not lose any information about the blasts in between frames, as they can be fired on both even and odd pixels. This all results in a starting size from 210 by 160 going down to the final array size of 170 by 134. And before this is input to the model, this matrix is reduced to or is flattened to a vector of about 23,000 values. The current iteration of the model is very simple. It includes 3 layers: the input layer, the hidden layer, and then the output layer. Something different from the Pong code is the fact that instead of having a binary action that can be represented by a scalar value, the model outputs an array of probabilities for each of the 6 potential actions that have already been discussed. And this complicates things somewhat. Essentially, in order to choose an action, the weights are determined, the weights for randomly sampling from the action space are determined by the model, and then one specific action is chosen, again partially at random, although the probabilities vary, and this is what actually advances the environment. This requires a softmax activation function as the final layer rather than a sigmoid, and this each pixel in the image after being flattened is associated with 128 different neurons, and slight change, instead of using a ReLU, a rectified linear unit activation function, a leaky ReLU, which retains some of the values of the neurons below 0, is used. So in order to evaluate the later performance of the model after it is actually learning, it's important to note the performance when the model is randomized, when it's in its initial state before any backpropagation is applied. In this case, the score averages out to roughly 100 points per game. The probabilities, as seen in this lower graph, the probabilities are consistent. Since they're randomized, it's a 1/6 chance of choosing any one of the 6 actions, and there's a decent amount of variability even both in the random and later in the trained states. Outliers can occur, however, not just because of the general possibility, but because of the fact that rewards escalate later into the game. So killing one demon in one of the later stages is more valuable than killing every demon in the initial stages, and this can create a sort of extended variability in the actual scores we see. So for the initial training stage of the model, everything was split up into batches of 64, and I'm going to present these in graphs of 10 batches, so 640 total episodes. Essentially, the model performance very slowly picked up. There were very visible changes, which I will address later. However, it took a while for the model to start improving from a random, where initially still the values hovering, scores hovering around an average of 100 points. The trend of a slight but not very significant increase in performance tends to continue until roughly the 900th total episode. And then there's a very sudden shift where the variability increases rapidly, the minimum values start to increase quite a bit. And so overall, the scores, the average, a moving average of the scores represented by this red line, increases very quickly, going out from about 1,000 episodes of training. However, after about the first 1,300 episodes, the performance increases slightly but starts to plateau. Eventually, the model reaches a pretty consistent stage where the average performance is not adjusting that much, and this is suggesting that after about 1,500 episodes, the performance you can expect is around 400 to 500 points a game as compared to the initial 100 to 200 points per game that occurred when the network was just completely randomized. So one of the major problems I came across when training this algorithm was what I refer to as corner stalling, where the agent will move to one side of the screen or the other and will not really leave that area. And the problem is the demons in this game are not completely random. They also choose to stick to one corner of the screen or to stick to the center. And so what will frequently happen is the demons will never ever cross back into where the ship is, into the corner the ship is in. Being on the opposite corners means there's no interactions and no rewards gained, but the ship is not at risk of dying either, so the game just continues to infinity. To address this, I changed the noise function, where the noise being added to the probabilities predicted by the model becomes proportional to how long it's been since there's an interaction between the demons and the ship. So that way, if it's been a very long time where the model is stuck in this loop on one corner or the other, then the ship is more encouraged to take more randomly generated approaches to get closer to that 1/6 probability of each interaction, and that way the chance of returning to the opposite corner where the demons are is increased. And similarly, this can be done using the same metric of whether or not the ship is stalled. The probabilities for moving left or right can be reversed so that instead of getting stuck in the left corner, the ship will actually be encouraged to move to the right corner. Another problem that just affects the converging of the model is the fact that the rewards are not completely intuitive, whereas the score only reflects the positive instances of killing demons. However, it doesn't reflect the fact that the ship shouldn't be caught in a loop. It shouldn't be giving away lives, dying easily, and it shouldn't be shooting unnecessarily either. And so in order to sort of address these things, the loss of a life in an episode is a negative reward, and similarly shooting without actually hitting a demon is a small negative reward. Aside from the actual quantitative scoring, there is a very noticeable trend when viewing what the model is actually doing, when rendering the actions being chosen by the model. The first thing is that there's a very sudden shift between random movement back and forth to choosing the one corner or the other, as I mentioned in the corner stalling slide. This is one of the first changes that happens after the initial batch is back propagated. Interestingly enough, after the second batch, the model actually chose to have the agent switch sides, where the probabilities shifted suddenly, whereas it was first biased towards staying in the right corner, it then became biased towards staying in the left corner. Later iterations started to add in less movement and less blasting, so there's actually much higher probability of choosing a no operation action where the ship would simply stay where it was and not fire any blasts. Again, the blasting frequency starts to lower as the model trains more. Initially, the ship was just blasting as frequently as it could. Unfortunately, the model never really converged to a place that is similar to what we might expect from a human. Instead, it's sort of maintaining this trend, but doing it a little more accurately, where it's sticking to a corner, it's shooting intermittently, and it's not moving unless it really seems to have a reason to. And for the most part, it's not moving at all. It's staying just a little bit from the side of the screen. To wrap this up with a few references and next steps, currently the problem is the model just not replicating this human behavior, as I mentioned in the last slide. Not that it has to replicate human behavior precisely, but that it doesn't seem to have an understanding of evading the demon's movement and adjusting to the environment, rather sort of sticking to a singular strategy throughout the entire episode. In order to try and improve this, a couple things I'm attempting to address is the noise generation, adding some complexity to how the noise is being generated to better encourage some of these behaviors that will benefit the model in the long run, to reevaluate how the rewards functionality is, to empirically test if the addition of negative rewards is positive or negative. That hasn't been done to a sufficient degree, and whether increasing those negative rewards will result in faster or slower model convergence. And aside from that, the opportunity to add in things like max pooling and extra layers to the model to try and address some of the more complexities in the input space. Those are all potential options for improving performance.